Welcome back to my Commodore 64 Memories videos. This is where I look at old Commodore 64 software and some of the technical details behind them. Today we have Lode Runner, released in 1983, created by Doug Smith and the conversion by Dane Bigham. So yes, wow, I think I was 10 years old, or maybe even just 9 years old when this came out. But I did play it to death, I seem to remember, way back in the day. Here we are in C64 Debug GUI, and it doesn't auto-start. What do we have? Oh my word, we've got a basic program which seems to have some data at the beginning, and then some prints, and then a read loop, and then a sys. Gosh, okay. So it's just running this code which is inside these data statements at the beginning there of the program. My word. Okay, this is definitely retro. I also don't see any disk protection code running. So, okay. No disk turbo, no nothing. I mean, this was 1983, so it's kind of to be expected, I guess. We'll wait for the game to load, and in the meantime, we'll put it onto this screen here so that we can see in this version of C64 Debug GUI, it will display little red bounding boxes around any sprites that are on the screen so we can see how the screen is formed. Same for this screen as well, but this one shows all of the VIC debugging and CPU opcodes and stuff like that. This is the full memory map, and it's just showing us how much is being loaded and how slowly it is. Oh look, we've got a couple of sprites, but they're hidden away in the border, but we can see where the sprites would be because of the red bounding boxes. Okay, we've got what looks like a nice functional bitmap credit screen, loading screen, I guess. This is the disk version, of course. Now, I really liked this kind of circular, what is it, dissolve, fade in, I guess. No, it's a dissolve, right? Or transition between the screens. A nice little self-playing demo as well. We can instantly see where the sprites are. The sprites are small, but they definitely have character, right? They're high resolution as well, by the looks of it. We've got usually, the score, men, lives down at the bottom. The objective of this game, and I'm not very good at it, is that you have to collect these cube things, boxes. I guess they're treasure. And then once you have collected all of them from the level, then a ladder appears, and then you can go to the next level, usually above, I think, right? Oh yeah, you can move across the rope as well. Not doing so well. I'm getting cornered. The trick is to try and group these enemies together so that they're not attacking you from lots of different sides. Okay, that one ran away. Thank goodness. Okay, I think, wow, am I going to be able to complete the level? Oh, come on, come on. Oh, no. Oh, dear. Oh, what have I done? Okay, ooh. Oh, ooh, yes, I can run across. Oh my word, I've completed the level. That's a real surprise because I'm actually terrible in this game. So the screen kind of like dissolves away afterwards in this nice circular fashion. It's a little bit slow, to be honest. It could have done with having a press fire to skip the effect thing, right? But hey, there we go. And then you get the next level. If I pause the game and move the targeting cursor around, you can see where the sprites are being updated. There's no multiplexing going on. Just a normal kind of like standard bitmap screen in the background with high-res sprites over the top. There are those 4 sprites there that are active in the VIC debug view there. So nothing really too much more interesting. Let's have a look at this in ICU 64. Let's disassemble that code which was poked in from the The basic starting program. Okay, it's just doing a bunch of JSRs. Looks like it's doing a set LFS, set nam, and load. Yep. And that means it's just loading data from the disk, and it's probably just loading these two files because the first file on the disk is the loader. Let's see if there's any drive code running. Let's reboot the game, reboot the disk. There's no drive code running at the beginning. Let's warp all the way through. There we go. That's why it's loading quicker, is because I've got warp mode enabled, roughly 10 times faster. And there's a bit of disk access, but there's no drive code running, I don't think. No, because I did put that that ranged breakpoint right in the drive device. So we can see when the level is calculated, there's quite a lot of calculation going on in the background. Ah, look. Okay, so the sprites are in the first bank, and we can see that, well, we've got dynamic sprites there, definitely. So we have, wow, okay, so we seem to have a sprite being calculated into temporary memory, and then that temporary sprite being copied into dynamic slots of sprites. Let's have a look at the bitmap screen in the bit debug view there. Okay. So the bitmap screen is multicolor, but the sprites seem to be single color, high resolution sprites. Yeah, that's not terribly sensible, is it? So let's move. This is the bitmap screen, which is also in the first Vic bank, which is being displayed along with the sprites. We just leave that there zoomed in so we can see what the game is trying to render. So yes, we have those dynamic sprites and we have a temporary sprite being calculated. So let's use the debugging tools to see if we can find out where the code updates the sprites and also draws into the screen, rather the bitmap screen, rather. So that's what 00004000800C00. No, not C000, right? It's 0C00. Each row on the debug graphics map for the sprites view there is 400 in hex bytes, because it's just that number of sprites horizontally. So now, there we go. The watch store point on C00, which was that first dynamically calculated sprite frame. And it seems to be copying from 5B, and there's 5B there in the ms command, which is memsprite, which dumps the sprite using ASCII characters. So let's see what stores into 5B. So that routine there seems to be copying from temporary to active sprite frame, right? And then this code here, ooh, okay, so we stepped out of the copy. So let's actually add a label. I've done this before in some previous videos where I've added labels once the purpose of a routine is discovered. And this is quite a good practice to use, of course, because it helps you when you're looking at the disassembly view. And it means that I don't have to remember all of these hex addresses and what they do. So yeah, anyway, let's see what happens. Aha, okay, so here's the code which calculates data. It's not doing a straight copy. It calculates data into that temporary sprite memory at 5B, all the way down in 0 page. It seems to be reading from one 256 byte page, and then another one at A400, A500. Looks like there's another one just down on the bottom as well. Looks like it's scrolled off the bottom of the disassembly, so that looks like there's a third store as well. Let's have a look. So it's setting up an address into D indirected, D and E indirected with 0 page addressing. There we go. Oh, it's storing into 5B, storing into 5C, and then it's ORing data and then storing it back into 5C and 5D. It looks like it's calculating the sprite from kind of like different format graphics, maybe partially compressed, maybe it's different format graphics that came from a different platform, perhaps. And that's why it's apparently calculating two kind of like vertical columns at the same time by doing an OR together, perhaps. Or maybe it's merging two sprite frames together from two different halves of animated sprite data. Maybe. But anyway, it's not a simple copy. So if you wanted to try and get all of the sprite frames from this game and edit them and then put them back into the game, for example, which is what the person asked me, if it was feasible to look at tools which did this or would do that, it would be quite difficult because the sprite data seems to be compressed or at least stored in a way in memory, in a format in memory, which is not obvious and is non-trivial to figure out. I mean, it would certainly be possible to figure out the encoding method, but that would take a bit more effort and a bit more time than what I'm going to be putting into this video. But yeah, definitely anyway, a non-standard format in memory for the dynamic sprite frames. So with a breakpoint on this calc working sprite routine and advancing for each run up until that breakpoint by using the X command, I can see that there's some self-modifying code which self-modifies those. They were, what was it, A4 and A5, right now it's A6, A7, I think it was. There's an input coming into this routine, and the input seems to be coming in 0 page memory location 23. So let's look at location 23 and then advance the game execution, but stopping at this breakpoint each time. Yeah, okay, 23 is different on each execution of this calc working sprite routine. So it seems that maybe possibly that the sprite frame to decompress or whatever it's doing or convert is coming in from 0 page memory location 23. And then the result of that decompression or conversion of the sprite data into the temporary working area then copies it into the dynamic sprite frames for its destination. Now, there's that second bitmap in memory, look. That's in the second bank. It was starting at 4,000. So there's the first one. There's the second one. First one, the game view. And then the second bitmap, there we go. That seems to be the that's the calculated level data or the calculated decompressed map screen, right? So if I exit, let's get rid of the breakpoints. There we go. If I let the game run now, let's see what happens with that screen. Okay, so I died. You can see that the rendered game screen on the bottom right-hand debug view there reflects the dissolve effect. Okay, great. And then the game over animating thing as well is just animated straight into the bitmap. Fantastic. So I don't know if you saw that, but basically the level calculated from the bottom up on the bitmap debug graphics map bitmap view there in the top right hand corner of the screen. Well, that's intriguing. So it seems to calculate the level view first and then do that dissolve into the rendered screen. You would kind of expect that, right? So the working bitmap is in the second bitbank at 4,000. Let's see if anything is, or let's see where the code stores into the rendered VicBank, rendered bitmap in the first VicBank, which is the screen. Well, that's intriguing. There seems to be code which is reading from the temporary sprite area and EORing it, so it's creating like a mask from what looks like, well, it's not high-res decompressed sprite data. It looks like it's being converted into a multicolor mask. Why? Why is it creating like a multicolor mask from the high-resolution sprite data in 5B, the temporary calculated sprite? And why is it then anding it, using that sprite-based mask, why is it then anding it with F and 10 indirected? That is the rendered game bitmap. So it's taking the sprite mask and it's chopping out a hole in the from the game bitmap data. It's ORing in the originally calculated non-drawn bitmap, and then it's storing it back into the game bitmap. So why is it doing that? Because we're using hardware sprites. This game uses hardware sprites. We know that because we've seen the red bounding boxes. So there is no need to mask out a hole based on the player's high resolution sprite, especially since it's being converted into multicolor mode. I don't know why the developer would have done this. Maybe the developer didn't really understand how hardware sprites work, and they thought that they had to mask out the data behind. So anyway, let's fill the rendered game bitmap with a color. Oh, I just died. Oh, well, you can see, look, from that happy accident, the dissolve effect doesn't update the full screen. It just updates the needed pixels. So anyway, let's get my player character, up towards the top of the screen. Okay, now let's fill the game rendered bitmap. Look at that. As the player hardware sprites move around the bitmap, that code is basically carving out multicolored pixels from the filled game bitmap screen by using the backup. So it's selectively restoring pixels using the pristine backup copy of the bitmap, which is in the second VicBank. Well, that's really very, very odd. I've not played this game a lot, so is there some kind of like game mode where the player has to walk around a dark level and it gets revealed with like a light or a lantern or something like that? I don't know. If you know if there's a light or lantern level in this game, then you can probably put a comment in the comments section below and let me know. But otherwise, I don't know why the programmer would be restoring multicolored pixels based on the sprites, hardware sprites that are moving around. Maybe, possibly, this game started off as a purely bitmap game. And maybe, possibly, the purely bitmap game, because it's a multicolor bitmap, maybe it was using multicolor sprite frames for the characters. And maybe the programmer thought it was too chunky. And maybe the programmer then discovered that they could use high-resolution sprites, and then they forgot to remove this code after they implemented the hardware sprites version of the game. That might be a plausible, logical explanation. Although, terribly forgetful, right? If you start off with bitmap sprites, bitmap-based software sprites, basically, and then you progress into using hardware sprites, but then you forget to remove the code which restores pixels in your bitmap screen, rendered bitmap screen, then yeah, that's a bit funny. But anyway, that might have happened. So that's interesting. That seems to be some, I don't know, legacy code or something like that. Or it would be used for a mode of the level, game level, where the level reveals itself as the sprites move around the screen. So yes, if you like these kind of technical deep dive videos, then please do consider liking or subscribing to this channel, or sending me a super thanks. They are always very much appreciated. Take care, have a great day, evening or night, wherever you are.